let me explain the problem statement and yeah. So what he's trying to say is actually this is a problem on stack. So yeah. So what he's trying to say is you will be
Now,
given
have
an
you
array.
started the recording?
Yeah, I have started.
Okay.
Where is it? Okay, so you will be given an array. Yeah, so you will be given an array. Let's say array is 3, 1, 2, 4. This is an array. We need to find out, uh, if you closely see here, find sum of min b, b ranges on every continuous subarray. So what he's trying to say is you will be given an array. Uh, First of all, generate all the subarrays. We need to find sum of minimum values on each subarray. Let's say here you have 3, 1, 2, 4, right? So you have subarrays are 3. If you closely see, these are the subarrays. So you have 3, 3, 1, and 3, 1, 2, 3, 1, 2, 4. Then what you will have? 1, 1, 2, 1, 2, 4. Then you have 2, 2, 4, and 4. So these are the possible subarrays, continuous subarrays you could make. Now in each subarray, what is the minimum value? So in this subarray, the minimum value is 3. Here also 1. Here it is 1. Here also it is 1. Here it is 1. And here the minimum value 1. Here also the minimum value is 1. Here it is 2. Here it is 2. And here it is 4. So now we need to make a sum of all these. So if you see 3 repeated one time, okay, let me sum all. So 3 plus you have 6 ones, right? 1, 2, 3, 4, 5, 6. So 6 ones plus 2 twos plus 4 plus 1, 4, 4. So which is going to be 17. So that is the expected answer. So he just wants us to return the sum of minimum values in each subarray. So that's the expected answer. But he is saying that the answer could be very large, so that you can return the answer in the form of modulo. So whatever answer you generate, it can be generated modulo of 10 to the power 9 plus 7. Okay, so this is what in this case obviously it is going to be 17. So the answer could be very large. So return the answer in the form of answer modulo by 10 to the power 9 plus 7. Do you understand the problem statement, Kalyan Ajay? Yeah.
Yes.
So what is the brute force approach here? What could be the brute force approach here? What could
Find
be the
all subarrays, then find the minimum and make
yes?
some.
So find all subarrays and yeah, in each subarray. So what could be the minimum value? And just sum all the minimum values. Return result by 10 to the power 9 modulo plus 7 value, right? So this is the brute force approach. So what is the time complexity here? What is the some time complexity here? First of all, how many subarrays you can generate? So if the
2 to
input
the
length,
power n.
no, that is subsets, right?
Okay.
Subsets. So if there are n, so at max you can generate n squared subarrays. So definitely it goes around, you'll get n squared subarrays, and while generating the subarray on constant time you can find out a minimum value. So obviously it is going to be big O of n squared, more or less equal to. But let me tell you, the optimized solution for here. You have 3, 1, 2, 4, and we need to find, we need to generate all the subarrays, find the minimum value of each subarray. But if you closely see here, right? If you closely see here, you have how many times 3 came? one time, right? So 3 came as a minimum value one time. How many times 1 came as a minimum value? 6 times, correct? So here 1, 2, 3, 4, 4, 5, 6, right? And how many times 2 came as a minimum value? 2 times. And 4 came as a minimum value as 1 time. So if you closely see, which is going to be 1 into 3 plus 6 into 1 plus 2 into 2 plus 4 into 1, so which is equal to 70. Is this clear what I'm trying to say, Ajay, Kalyan?
Yes.
Yeah, Maithili, so what we are trying to do is, there is a problem statement 907. So what it is trying to say, simply generate all the subarrays for a given input, and find out a minimum value from each subarray and return sum of all the values. In this case, we generated these many subarrays, continuous subarrays, and each subarray, these are the minimum values. Sum of all the minimum values is 17. So when we calculate this, we understand that in all these subarrays, minimum value is 1. So 1 repeated 6 times. And in these subarrays, minimum value is 2, 2 repeated 2 times. Yeah, that's how it is. So we just need to find the sum. So on the brute force approach is, you can generate n squared subarrays, then find the min value and get the sum. That is one way. And let me tell you the optimistic solution. So this is what, now we understood that 3 repeated so now we understood that for a given output, 3 repeated one time, 1 repeated 6 times, 2 as a small element for 2 times, and 4 as a small element for 1 time. So now let's understand how it works. So this is my given input. So 3, 1, 2, 4. Let's take here. So if you closely see, one can be part of, if I start from 1 here, so from to the right, 1 can be part of to the right elements, 1 can be part of to the left elements as well, correct, in a generated subarray. Yes or no? If you closely see, if I consider only right part from 1, if I consider only right, so then it is going to be 1, 1, 2, 1, 2, 4, right? Correct, nobody? So to the right. Similarly, if I consider 1 to the left, so it is going to be 3 comma 1, right? Correct, na?
Yes.
So 3 comma 1, 3 comma 1, or 3, 1, 2, 4, or 3, 1, 2. So it can be anything, right? So you have 3, let me note down. So if I consider left part, so 3 comma 1, that's it. So or 3 comma 1 comma 2 and 3 comma 1 comma 2 comma 4. If I consider only right part, so 1, 1, 2 and 1, 2, 4. That's why you got 6 elements here. You got 6 subarrays, and in each subarray the minimum value is 1. So that's why we got 1 repeated 6 times, right? Now if you closely see, okay, let me keep this. Yeah, so if you closely see, yeah, so this is what it is. Let's move on here. So this is my 1, right? From 1 can be part of minimum value in the left part, 1 can be part of minimum value to the right part. It can be any possibility. Now let's understand. So this is my 1. Find out what could be the previous smallest element, comparatively 1. So there is no previous smallest element, right? If I go left, correct? Yes or nobody? To 1, do you have previous smallest element? No, not
No.
please. So you have a previous smallest element. Similarly, to 1, what is the next smallest element? There is no next smallest element, right? Yes or no? Do you have next smallest element
Yes.
to the 1?
No.
No, right? So it means, if I ask you what is the previous smallest element, so previous smallest element, so there is no previous smallest element. So definitely we already know, right? So if you don't find previous smallest element, so which is going to be minus 1, and to 1 the next smallest element, so this is my next smallest element. So uh, do you know, right? So you understood the principle, right? So for previous smallest element we already calculated from current index. So this is index at 0, 1, 2, 3, and you will have 4 here. It is representing n. So if I want to find out what is the previous smallest element for this, for a given one, so current element is the next smallest element, so it is going to be 1 minus minus 1, because there is no previous smallest element, so minus 1. So definitely you have 1. Okay, so you can derive a logic, but I will tell you the algorithm, so that if you already practiced previous problems, you can easily derive the logic. So if you closely see from this one, considering this one, so you will have this one prior to this one, so you have two elements because there is no previous smallest element, and after from this one, after if you go right, you have including current one, you have three elements. So from 1 to the right you have three elements, from 1 to the left you have two elements, because there is no previous smaller element. So the number of continuous subarrays you could make equal to into 3, so which is going to be 6 into 1, so which is 6. So this is one way. Similarly, if I want to find out for 2, so let's say 3, 1, 2, 4. If I want to find out for 2, so I want to find out what is the previous smallest element. This is the previous smallest element, right? Yes or no, buddy? Yes or no? With respect to 2, with respect to 2, so there is no previous smallest element, right? 2 is going to be the previous smallest element, right? So there is no element prior to that, correct? Yes or no?
Yes.
So there is no previous smallest element, so that obviously for this the previous smallest element is 0 at 0th position, because this is the correct. And if you go right, what is the next smallest element? There is no next smallest element, right? Yes or no? For 2 there is no next smallest element, right? Correct, Ajay?
Yes.
So obviously you will compare n minus 1, so obviously you will get 2 here, right? So definitely you will have only two elements to the left, so which is going to be, it means, what does it mean? So this 2 repeated 2 times, so which is going to be 4. So to the left you don't have anything, so that you just ignore this. If it is 0, you just ignore it. To the right you have two elements, 2 into 2, which is going to be 4. So that's how we calculated, right? So 1 repeated 6 times, 2 repeated 2 times. Similarly, if you go for 4, for 4 there is no previous, there is no previous smallest element, but for right there is no right, so obviously you will get 1 here, so 1 into 4, which is going to be 4. So similarly for 1 also, previous there is no previous, and even to the right there is no, to the right you have a smallest element next to it, so that's why here you will get 1. So hope you understood the concept. So the concept is, find out for a given index, for a given element, find out what is the previous smallest element, what is the previous smallest element, what is the next smallest element. You will find a count. So once you get a count, so the count, so if there are no previous smallest elements, so then it is going to be current element, so 1 into, and what are the next smallest elements, take that next smallest element count. You will get the number of times this element can be minimal, and just take that, for example in this case, for 1 previous you have 2, next you have 3, so 2 into 3, which is 6. So 6 times this current element can be minimal, so 6 into 1, which is going to be 6. So that's how you can easily calculate and get the sum. Is that conceptual understanding is clear? Ajay, Maithili, Kalyan, is that clear? Yeah, so find that and solve this problem. It's a very good problem on a monotonic stack, which is exactly same as this 84 and 85. So it is almost same as that, but give a try. If you are unable to solve it, let me know so we can discuss. Okay, nice. So let's move on. Let's start with Q. Okay. Okay, let's start with Q. So what do you mean by Q, right? So Q is a first in first out concept, right? So for example, these are the elements you have in the queue. This is E1 and E2 and E3. So this is also one side. So first, so this is what we call first in first out. So whatever element you insert, which will be removed first. So we call this operation as DQ, and you
So,
always.
sorry to interrupt. Are we recording this?
Yeah, we are recording.
Okay.
Yeah. So we keep on add elements, right? So always we delete elements from front and we add elements from last, right? So this is the concept of queue. So it is a first in first out, right? So whichever element which is inserted first, so which will be removed first. Now if you want to implement a queue, how do you implement? For example, I added 1, 1 will be added, then I again added 2, 2 will be added, then I again added 3, 3 will be added. Now I want to delete, or so that in queue the delete operation can be called as pull or delete. So let's say I want to delete. So if I want to delete, so this is going to be deleted. Now queue contains only 2, 3. Now again if I want to delete, so then this 2 will be deleted, then this is going to be my queue. Now if I add of 4, then this is how it becomes, right? So in the queue, the first element can be called as front, the last element can be called as rear. So how do you design a queue if this is the use case?
Srinu, when we are adding that element 4, will it not be coming at the beginning of the queue?
Because that's what I said, right? In a queue, you always add elements at last and
Okay.
you delete elements from first.
Beginning, okay, got it.
So if this is the case, how do you design a queue?
We can design it using linked list.
If you closely see, queue is nothing but linked list only, right? Yes or no? So you have, so first you added 1, okay, so 1 is added, so we call it as head, and this is also tie. Then you add one more element, then it becomes 1, 2, and this is my head and this is my tile, correct? If I add one more element, then 1, 2, 3, then this is my head and this is my tile. So you keep on move the tile. Now if I remove, if I delete, if I call delete method, so what you do, you just move the head to the next element, so that head equal head dot next. So you have 2, 3, so this is going to be head, this is going to be tile, correct? Correct na?
Yes.
Maitri, are you clear? Yeah. So it's a concept of simple linked list. There is no complexity here. So this is how the queue can be implemented. So the add operation is always going to be constant because you just add a node to the tile, and delete operation also always going to be constant because you just move the head to the next element. And if you want to search, so definitely you have to traverse all the nodes, so which is going to be linear. Okay, so that's it. That's how the queue works. Now if I want to design a queue using stacks, how do you design? So we want to implement a queue using stack. How do you design? What is the concept of stack?
Last in first out.
So stack is last in first out, right? So whatever element you inserted last, that will go first. But queue is first in first out, right? But we want to design a queue using stack. So can you, first of all, how do you want to do that? Is it possible with single stack?
With two stacks, I think we can do.
Sorry?
I mean, like with two stacks, maybe we'll be able to achieve.
Okay, if you want to do it with the single stack, so what is the problem you could face?
We can only push it from the top, but we cannot pop the element.
Yeah. Okay, if you want to pop the element, then
from stack we can always pop the element from the top, but when it comes to queue we have to get that element from the end.
Then
But we
okay,
cannot
I
access
want
that
to
using stack.
implement with the single stack. Then what is the problem you face? Can't you implement with single stack? That is the case.
We cannot pop the last element from stack if you're taking one key stack.
Okay, so let me see with single stack. So I go with single stack. Let's see what are the complexities we could see. Then we will try to address it. So let's say I have added element one. Okay, so let me remove. So add of one. Okay, so if you do add of one, so what will happen? What will happen? So one will be added to the stack. Then I try to add 2. Okay, then 2 will be added to the stack. Then add 3, then 3 will be added to the stack. Now I just wanted to delete. So if I wanted to delete, then what is going to happen? I need to delete this one, right? Correct? It's a queue now. So I want to design a queue through stack. But with respect to queue, I need to remove the whichever element which is inserted first. So 1 is inserted first, which is to be removed. Then what should I do ideally? What should I do ideally? Tell me.
You have to pop out all elements and insert
Okay,
into
so I need to
one more
pop
and-
all these elements. So okay, if I pop, it is going to be 3, 2. Then last element can be removed. Correct?
Yes.
Correct? Now again if I want to delete, then what should I do?
You can simply delete from the second stack.
How do you know that?
As you are inserting into one more stack.
Okay, but it's a single stack only, na? S1. Then again S1 will be reassigned to this. So ideally what should be the reason? So ideally what will happen? Ideally what you should do, so first you load all these elements into temp stack. Okay, so you load all these elements into temp stack. Then what happens? You delete the last element and you again load these back into main stack, so which is S1. Let's say that. Then it is going to be 2, 3, right? It is going to be 2, 3 again. Now if you closely see, if this is how it is, this is how it should be, then what is the time complexity of delete? Add definitely takes linear constant time, right? Yes or no? Others, please.
Yes.
What is the time complexity of delete?
Order of n.
So order of 2n, right? So what will happen?
Yeah.
First you load n elements to the temp stack. Then what will happen? So order of 2n, so it is 2n. So you load n elements to the temp stack and again you load back to the main stack so that your order will be preserved, right? So in this case the delete operation is getting linear and add operation is getting constant. Now how do you improvise it? So what is the problem you could see here? Yeah, can you understand what is the problem you could see here?
The loading of all elements into temp.
Loading of
and
elements, right?
That. Yeah.
Right. If you closely observe, right? If you closely observe, when you load elements into another stack, does it not looking like a queue? The temp stack, right? The temp stack, does it not looking like a queue?
Yes.
Yes, it is.
Then catch is there, right? It means what you need to do. Okay, so I have a one stack. So one stack is for pushing the elements, other stack is for deleting the elements. Okay, so it means let's say the same concept. So let me explain the same concept. So you have two stacks. So you can say nq stack, so which will for adding elements, and you will also have dq stack, which is for deleting the elements. Let's say I have added 1. Okay, so you added 1. So whenever you add an element, blindly you keep that element into the stack. Okay, nice. Now again I have added 2. Again keep that 2 into stack. Again I have added 3. Okay, so keep that 3 into stack. Now my nq is having 3 elements. Now I want to delete. So when I want to delete, I will verify my DQ stack. Okay, so my DQ stack is empty now. So what I will do, I'll pop all these elements from the NQ stack and load into DQ. So I'll pop all these elements, load into DQ, it becomes 3, 2, 1. Clear? 3, 2, 1. So now, is it my DQ stack is a queue? Is it not this DQ stack is a queue? Is this a queue or not? Because it's a reverse of this stack only, na? Yes or no? For example, now I want to delete. So what I will do, I will delete this element 1. Done. 1 is deleted. Now again I add 4. So when I add 4 in my NQ stack, I will just add element 4. Okay, so let me erase this. I'll just add element 4. Again I'm trying to add 5. Okay, so add 5. Now I call delete. Now if I want to delete, do I need to load these elements into DQ stack?
No, we don't need to. We can delete directly from DQ.
Correct, right? So because if you see, you have 5 elements, right? You have 5 elements, 1, 2, 3, 4 and 5. So what you do, first you loaded these 3 elements into this stack and you deleted it. Now you are already preserving the order for next 2 elements, the first 2 elements of a queue, which is already present in the stack. So these 2 elements are not preserving the order. So what you can do, so when you call delete, you can blindly delete. So you can blindly delete this from DQ stack. Okay, again if you call delete, again you can blindly delete this from DQ stack. Now again if you want to delete, now you understand that all the whatever pre-populated queue elements which are already becoming empty from this DQ stack, now it's time for us to copy these elements from here, load here. So once you copy and load, so then again it becomes 5, 4. So it means 4, 5. Now again you can perform delete operation on this 4. Is that clear?
Yes.
Ajay, Maithili.
Yes, Srinu. Srinu, I think the screen is hung up, I think.
Okay. You can't see my. So whatever I
It
write.
is-
Okay, got it. There is some problem with the system. Problem is once I reconnect it, it is not connect. So it's giving problem on screen recording. It's not able to record the screen. It was happened for last session, right?
Last session didn't observe this issue.
For palindrome session, it was happened.